Oops. Well, just 1 second. Okay. I could use Kirchhoff's loop rule for solving this equation or solving this system, but I'm not going to do that. We've talked about phasors, and I want to use the idea of phasors to set this up. I'm going to draw a diagram. I'll set up my x and y axis. And really the goal here is to figure out what are the maximum values of the voltage across the capacitor, the voltage across the inductor, and the voltage across the resistor. My total current and my phase angle. Those are the things. And we can calculate the time dependence of V sub R, V sub L, etc. But I'm not going to spend time on that. Just part of it is because of the interest of time. We're a little bit behind. Really, and typically you're interested in the maximum values of the voltage drops and the current. And then the RMS values then are just the maximum voltage values divided by the square root of 2. The one thing to notice is that the current across each one of these elements is going to be the same. Okay, so all of them are going to have the same current through them because they're all in series. And the voltages across each element will have the same phase relationship to the current like we saw before. So what I'm going to do is I'm going to draw the phasor for I, for the total current. And I choose to do it along the x-axis. Let me draw I sub m there. Okay? All right. I could choose any angle, but the thing is it just makes it easier for me to draw the phasor diagram this way. Just imagine this thing's rotating many times a second, depending on what the frequency is. Okay, so the voltage drop across the resistor is in phase with the current. So let me draw the voltage drop across the resistor. There's an inductor and a capacitor in my circuit. The inductor has the same current going through it because they're in series. But the voltage across the inductor is 90 degrees ahead of the current going through it. So I draw my phasor 90 degrees ahead, like that. And then hopefully you can see this. I usually don't use this color, but I need this extra color today. It's kind of an orange color. For the capacitor, the voltage across the capacitor lags behind the current through it by 90 degrees. So I'll write V sub C. Okay, so now I'm going to put this together. These two are 180 degrees apart, so I'm going to combine the two. I'll draw the combination of the two right here because I'm going to use the head to tail method to add these together. So this, okay, so I'm going to get something about this tall. That's V sub L minus V sub C. And I'm going to add vector. I'm going to treat this like I'm adding vectors. And the sum of these two vectors, phasors, have to be equal to the power supply voltage. V sub m is the maximum value of the power supply voltage. So that's why I write V sub m equals V sub s, just so you know that V sub m, the maximum voltage, is equal to the power supply voltage. Okay? And then the phase angle is phi. then I readily see that this power supply voltage, V sub m, is equal to the square root of V sub r squared plus V sub L minus V sub C squared. And I can write all of these in terms of current. All right, this is current times resistance. This is the inductive reactance times the current. And this is the capacitive reactance times the current. And since this is common to all these terms, I can factor out I. And I call this thing in parentheses the impedance. So the impedance is the square root of r squared plus the square root of x sub L squared minus x sub C squared. Okay, so maybe let me write, I should write that down. And everything in here under the radical has ohm squared here, and this whole thing is ohm squared here. And remember, x sub L is omega times L. Oops, I gotta adjust the camera. Just 1 second here. Okay. And then x sub C is 1 over omega C. So this is the impedance triangle. And then from trigonometry, tangent of phi is opposite over adjacent. And since this has an, oops, V sub r. Since these have the I in common, remember omega is 2 pi times the frequency. Okay, omega is the rate at which we drive the power supply. Because right in this chapter, we're driving the circuit with a sinusoidally varying power supply. So it's every circuit we're going to describe in this chapter, we're going to drive it with a sinusoidally varying power supply. Okay? All right. So we have the expression for phi. I can write the expression for tangent of phi. I can write the expression for cosine of phi. All right, cosine of phi is r. Well, let's do it this way. V sub r over V sub m, which is basically r over z. Remember, the I is in common with all of these. And I can write an expression for sine of phi. Okay. There's my picture of the phasor in the notes. And it actually has the time-dependent expressions for the voltage across the resistor, the capacitor, and the inductor. And so our impedance then, like I said before, is Z. And I can call this like a generalized version of Ohm's law. If I write V sub M, the power supply voltage, as the total current times Z, where Z we call again the total impedance. And the total current then depends on R, L, C, and omega, the frequency of the power supply. And there's our impedance triangle. So I can draw the impedance triangle either with the voltages or with the impedances. So I can draw my figure. And really that picture tells you everything you need to know. Whether you use this, or actually, this triangle, or this triangle, doesn't matter. I mean, they only differ by a factor of the total current, right? Because this is I times Z, this one is I times R, and this one's I times X sub L minus X sub C. So they're the same thing, essentially. Okay. Remember that phi is measured with respect to the current here. It's positive for X sub L and negative for X sub C. And I drew this. This is important for you to understand. I drew this along the x-axis for another reason, that the projection of the total power supply along the I-axis represents what you would call the resistive part of the circuit. And it basically reacts more like a resistor. Whatever's projected on here has to do with elements that act more like a resistance. The projection onto the y-axis represents the reactive part of the circuit. But you can only say that if you draw your total current along the horizontal direction. And I'm not really being precise in saying what this represents along the x-axis. Okay, if I wanted to be more precise, then I'd have to tell you, okay, I'd have to write this, I'd have to write my power supply voltages, I'll have to write all my voltages in terms of complex exponentials. And if I do that, then the projection along the x-axis represents the real part, which means resistive. And the projection along the y-axis represents the imaginary part, which is the reactive part. Okay, and I mean, if you look at it, this is the reactive part. This is the projection along the y-axis. And then this is the resistive part, the projection along the x-axis. But that's true in general for any kind of circuit. Anything more complicated, you can say that. Okay? Because I gave you one homework problem that's a little more complicated, and I'm going to set it up for you before you actually, hopefully before you do the problem. I want to set that problem up for you because that one's a little bit harder, but I just want you to go through it. Okay? The methods you learn in the engineering class will be a little bit more efficient than solving more complicated problems. Okay. So, If this phase angle is positive, which is what I drew in this picture, what that means is V sub L is bigger than V sub C. If this phase angle is negative, that means V sub C is bigger than V sub L. Or X sub C is bigger than X sub L. Okay. So if X sub L is bigger than X sub C, then you have a high omega, high frequency for your power supply. And the current lags the voltage. Here's the current, here's the voltage. This vector is behind this vector. But if we're dealing with low frequencies, X sub C is bigger than X sub L, then the voltage will be behind the current. If these two are equal to each other, when are they equal to each other? Well, I mean, you can just set 1 omega times L equals 1 over omega C. You get omega squared equals 1 over LC. And so omega is 1 over the square root of LC. Oops. So if you set the power supply at a frequency that's related to this equation, in other words, F equals to 1 over 2 pi times 1 over the square root of LC. So if you have the frequency satisfy this equation, then what happens is this is 0. And all the voltage is across the resistor. Doesn't mean that the voltage across either one of these is 0. Oops. Let me make that smaller. That better? Okay. Like I said before, it doesn't mean that either one of these is 0. It just means they cancel out. And it's possible that these voltages are bigger than the power supply voltage. But if you actually take a voltmeter and measure the voltage across here, measure RMS voltage, and then you compare it to here, the voltage between these 2 points will be 0. The voltage across this guy will be the maximum power supply voltage, or the RMS voltage of this guy if you're using a multimeter. And the phase shift, if the difference between these two is 0, the phase shift will be 0. The current and voltage will be in phase. This is called resonance. You get maximum energy transferred to the resistor. Maximum energy delivered to the resistor. Of course, you're also using up the most energy because all energy is going to the resistor, right? You get maximum energy transferred to the resistor. You get maximum energy loss in each cycle because the resistor dissipates energy. Okay? And so there's a few things I want to say about the resonance condition as we proceed. Questions so far about this circuit? So suppose I wanted to find the voltage across this combination. Since they're 180 degrees out of phase with each other, the voltage across them is the difference in these two values. You'll be doing the lab. You're going to actually set up this circuit, and you're going to be measuring the voltage across each one of these. You'll set this to, let's say, about 2 volts. You'll find situations where you'll find frequencies when you adjust the frequency of the signal generator where the voltage across these guys is bigger than the power supply voltage. That's okay. You're still conserving energy. All right? And in fact, if you look at this circuit, let me rearrange the components. Actually, no, I don't have to rearrange them. Let's look at this. Let's look at the voltage between these two guys. Let's look at the voltage between these two elements. Let's say this is 10 volts and this is 5 volts. The total voltage is not 15 because their voltages are not in phase with each other. In fact, their voltages are 90 degrees out of phase with each other. If I want to find the voltage across these two, I actually have to complete the triangle here. So if the voltage across the resistor is 10 volts and the voltage across the capacitor is 5 volts, then I have to use the Pythagorean theorem to calculate the voltage across these two together. Does that make sense? Because they're not in phase. You just can't add them like that. You just can't add them like numbers because they're not in phase. And I've given you some homework problems where you're going to have to use this idea and understand this idea. Okay, most times students do this the first time. They think, oh, this is 10, this is 5, the total is 15. No, you can't do that because they're not in phase. Okay? So let me write some of this stuff down on this board. Let me redraw my impedance triangle. So I can write the total current the following way. Okay, and again, that represents the maximum total current. That's half, yeah, so these are half the peak-to-peak values, also known, they're the amplitudes. Okay, Patrick? We're just talking about the amplitudes. We generally don't talk about the peak-to-peak. Yeah, I mean, the instantaneous voltages would add properly, but I mean, you'd have to write out the terms explicitly, right? I mean, so you would have to write. You'd have to write the following. So that would give you the time. That would do it as a function of time. If you manipulate this, you'll get the expression. You'll get the expression for the total voltage. You can rearrange this using some trig identities, which are a pain in the butt to do. But you can rearrange this so you can write it in terms of the square root of v sub r squared plus v sub c squared. Okay? And again, we're generally, when we're analyzing AC circuit, we're really looking at the phase angle and the V's. That's really what we're looking at. The amplitudes, the capital V's. Okay. All right. So what about power in AC circuit? So I'm going to probably say what's a little bit more than what's in the notes here. Part of it is because this is information that's relevant to the last lab you're doing. So if I want to write power, let's write power as a function of time. So all small letters. We'll start with that. Okay, we'll write power as a function of time, all small letters. We're assuming, so far we're assuming an ideal inductor and an ideal capacitor. The only resistive element is the resistor. Okay. So let's write in the explicit time-dependent terms. I'll write them like that. And again, I sub m is given by this expression. My goal is to find the average. I want to find the average over a cycle. So goal is to P average. So to do that, I'm going to expand this. First of all, let me expand this. Oh, I forgot my V sub m, sorry. So let me collect these together. And then let me expand this because I can use a trig function, a trig identity here. Cosine, cosine, sine, sine, right? The lowercase, these are the maximum values. Maybe I should write, right? The lowercase just represent the maximum value, the amplitudes or the peak values. Oh, this means I'm writing them time dependently. The lowercase I and the lowercase v represents the time-dependent values, whereas the capital letters represent the amplitudes. Okay, so I want to find the average of this thing. Well, these are time independent, and we want so let me distribute this through. I want to take the average of that. And really what I'm doing is, normally you don't have to write the subscript average because the brackets like that represent average. Anyway, just to make sure you understand that. So in order for me to take the time average of this, really I only need to look at calculating the averages of these two guys, this one and this one and this one. So the average of this function we already did. What's the average of this over one cycle? It's a half, right? We did this the other day. So the average of this term is a half. Now, what's the average of this function over one cycle? Well, if I plot this over one cycle, this is almost like if I use a double angle formula. Okay, I didn't draw it very well. What's the average of that over one cycle? if I drew it symmetrically. Maybe let me redraw it better. Let me draw it better. Yeah, the average of that is 0. That's the symmetric, I mean, the function's odd. The integral of an odd function over a symmetric integral is always 0. Okay? So this integral is 0. And this one ended up being what, half? We did this the other day. And so P average is I sub m V sub m times a half cosine of phi. There's a name for this. This is called a power factor. That's called a power factor. Okay? And we can rewrite it some more because this is by the way, this is a 2, sorry. This is just R over Z. And V is I times Z. And so P average is 1/2 I sub m squared times R, which should make sense to you because all the energy is being dissipated by the resistor. But what's 1/2 I sub m squared? Well, remember that IRMS is 1 over the square root of 2 I sub m. So if I square both sides, this term ends up being I RMS squared times R. Okay? All right, let me continue through the notes. So I have this all done in your notes, so you can gloss through it. And you can see all the energy goes to the resistor. P average I squared RMS times R. Yeah, it's the same equation. I mean, it's basically I squared times R, but it's an RMS value. Now, let's take a look at the current again. I'll come back to this in a minute. Our current, this guy here, is given by this expression. And if I wanted to write this more explicitly, the I sub m in this expression or over there is V sub m over the square root of R squared. Oh, that's an R. Plus omega L minus 1 over omega C squared. Okay. A lot of times what we do is we'll factor out the omega and the L from the denominator. So when these two terms are equal to each other, I'm going to call this omega naught. This is called resonance. I don't know if any of you folks are in 215 this semester. You've talked about resonance in physics 215. It's the same, mathematically the same idea. You get maximum energy transfer from the driver to the system. In our case, the driver is the power supply. In the case of a mass on a spring, which you learn in 215, is basically something driving a mass on a spring. Okay. So when this is 0, then just Z is R. This power factor is 1. That means phi is 0 at resonance. And you'll be looking at that in the lab you're going to be doing starting, that I'll talk about this week. You might not start it this week, but. So this is called omega naught, is basically the natural frequency of oscillation. This is the angular frequency, the frequency itself. This is the natural frequency of oscillation. Remember, we talked about this with the LC circuit, how the energy gets transferred between the capacitor and the inductor at a particular frequency. That's the natural frequency in which the energy wants to be transferred between the capacitor and the inductor. Okay. And I should call this F naught again. Normally what one does is they factor out the omega here and the L, and they end up writing this in terms of omega naught. So they'll write it, it'll look like this. Okay. Oops, I gotta lower this a little bit. Let me zoom out just a little bit. Okay. Okay with that? So normally you write it like, oh, I forgot the omega. So it looks more like that. Okay. And I'll do that with P in a minute. That's normally how one writes it. So then you can see what happens in terms of omega naught. And so when you do the lab, as you're doing the lab, I'll talk about on Wednesday, you're going to be fitting your data to this function, which is kind of a complicated function to fit to. So that curve fit is going to take a while for you to do. Okay? The denominator, so again, the denominator is basically this. I just factor out omega I just factor out the omega out of here, and then I factor out an L over here. This is the square root of R squared omega squared plus L squared times omega squared minus omega naught squared, the quantity squared. Okay. It's hard to read the bottom. I will, I'm going to do something like this with the power equation, so you'll see it a little bit better. Yeah, remember that if I factor out an L from here, I get an L times C. It's inside omega. The c is inside the omega. And again, let me do the power equation. I'm going to do the same thing with the power equation. Okay? And you'll see it. You'll see everything. Oops. This is a plot. This is a plot of current as a function of omega. Okay? And I've plotted it for a given value of L. Maybe let me blow up the picture. I've plotted it for a given value of L, a given value of C, and a given value of VRMS, and omega naught is about 10 to the 7th hertz. I plotted it for 3 different resistor values. And what you notice that if I reduce the resistance, the peak gets narrower and taller. Okay? The peak frequency is narrower and taller. Now imagine you use an LRC circuit for tuning a radio, to tune to a radio station. Which peak would you want? Why? Why do you want to use the 3.5 ohms? I mean, you're right, Patrick. Well, why do you want to use 3.5 ohms? Yeah, if you have, you're going to select that frequency, right? You want it to be tall and narrow. If you create, if you use an LRC circuit to pick out a radio station, and the peak is wide, you're going to pick up more than one radio station. Right? Your circuit is optimized to more than one radio station. If you make it tall and narrow, then your circuit is optimized to pick out a particular radio station. Does that make sense? So let's look at power. Let's look at power now. I'm going to go back. I'm going to go back to this equation, and you'll see where all this omegas come from. Okay? So let me start with this equation. I'm going to erase all this and put this back up at the top. And I'm really going to use this guy. And I'm going to first start by writing it with this expression. Okay. So let me square everything. So now I'm going to factor out 1 over omega. Then of course this omega, oops, this is squared. Because when I factor out the 1 over omega in here, this is squared, so I got to put the squared over there. Of course, this is going to go up on top. Then I'm going to factor out an L. I want to take out an L from here, it's squared, so I got to put an L squared. But 1 over LC is omega naught squared. Do you see what happened to the omega, to the C then, Morgan? I used the fact that I get omega naught is 1 over omega naught squared is 1 over LC. And then when we analyze circuits, when we look at power as a function of omega, we write it this way. We normally write it this way. It makes it a little bit easier for the analysis. And so when this is 0, when the difference is 0, when omega equals omega naught, you get maximum power. And if you want to prove that, the power is maximum, then what you do is say, okay, let's take dP average over d omega and set it equal to 0, solve for omega, and you'll see that you'll get omega naught. So that's a fun little exercise for you to try. So if you plot power, you get a graph that looks like that. In fact, the power graph is actually narrower. The power graph is actually narrower by a square root of 3. Okay. How did I pull out the L squared? I just pulled it out. I just pulled it out of here. That's where the L came out in the denominator. Or I just used the distributive law. Yeah, but isn't it squared inside the brackets? Oh, sorry. Yeah, it's squared inside the brackets, right? Where'd it go? It's squared inside the brackets. Okay, let me go back to the picture. So you'll see the same thing as R decreases, the power graph gets taller and narrower. And one of the things we do we define something called a quality of the circuit. Anytime you have something that behaves mathematically this way, we define something called a quality, Q naught. Okay? And one can show that the quality, Q naught, is omega over delta omega for the power graph. For the current graph, It's that expression times the square root of 3. If I have time in lab, I will show it to you. I'm not going to do it now. It just takes some algebra. It's really defined as omega naught L over R. So where does this definition come from? So I want to show you briefly where this idea comes from for the quality factor. Typically, it's of the order of 10 to 100. When we do in this class, I think for this lab, it's probably less than 10, the circuit you're going to be using. When you do the similar lab in Physics 215, although you're not going to do it if you're in 215 next semester, you're not going to do the lab. But when we're on ground, if we do something called a driven damped harmonic oscillator, and Q is like around 200. So let me tell you real quick where the Q comes from. Q is defined. Okay, Q is the defined quantity. Q is defined as this way. Q is 2 pi times the maximum energy per cycle divided by the energy lost per cycle. Well, the maximum energy in a cycle, I can write it in terms of the inductor. And by the way, we evaluated this at omega equals omega naught. Now, what's the energy loss per cycle? I can look at the power that's lost per cycle, but I want the total energy loss per cycle. Okay, so the energy loss per cycle is going to, or the average energy is going to be 1 over the period. The integral from 0 to t of I sub m, or basically I squared times r dt. But this is the average energy. I just want the energy loss per cycle. I know that this integral is 1/2 I sub m squared times r. If I multiply both sides by the period, then this is the energy loss per cycle. The energy loss per cycle is 1/2 I squared m times r times the period. The i's cancel. The 1/2's cancel. And I have 2 pi over the period times L over R. But 2 pi over the period at resonance is omega naught. So that's where this comes from. But one can show it's equal to omega over delta omega. So let me go back to the drawing. What the heck is delta omega? Delta omega is the width of the graph when you're at half the maximum. Okay? So you got to go to half the peak height and find the two frequencies at which half the peak height occur. Take the difference between those frequency values and you get delta omega. It's called the full width at half maximum. And one can show that omega over delta omega is equal to omega naught L over R. My goal, hopefully in the lab, is to show you that. Maybe not this week, but hopefully next week. Okay, so my goal is to show you that this is this is related to omega naught over delta omega in lab. I won't do it here. It just takes a little bit of work. Although in the homework, you will kind of see that because there's a problem related to this. Okay. So now that we've talked about power and stuff, we've pretty much covered everything for the Lrc circuit. What else can I cover? Well, I can hook up the resistors, capacitors, and inductors in parallel. What do I do then? What if I have a RLC circuit where they're really hooked up in parallel? Then what? How do you think I'm going to solve that? So how do I analyze that circuit? Every component is hooked across the power supply. I have to draw a phasor diagram. I know that the voltage across each element is going to be the same. So let me draw my phasor. I know that the voltage across each element is going to be the same. I also know that the voltage across the resistor will be in phase with the voltage across the power supply. So again, let me draw the phasor. For the resistor. Let me draw the power supply. Okay, not only is this the power supply, but it's also the voltage across the resistor, the voltage across the inductor, and the voltage across the capacitor. They're parallel. But I know that the voltage across the capacitor lags the voltage across the power supply. I'm sorry, let me rephrase that. I know that the voltage across the capacitor is 90 degrees behind the current. I know that the sum of the currents through each one of these is going to give me the total current. So let me draw the phasor for the capacitor. The capacitor leads the voltage. The inductor current lags the voltage. The sum of the two gives me that. And there's your phase angle. Okay? That's my phasor for the parallel RLC circuit. And so tangent of phi And this is going to end up being, because they all have the same voltage in common. And so I have drawn for you a nice phasor diagram showing you everything about the parallel RLC circuit. Make sure you understand this one too, okay? Make sure you understand this one too. So we can derive expression for phi. We can derive an expression for z. The exponents on the third line, the exponent minus 1/2 should be plus 1/2. Okay, there's a typo there. Let me go back to the diagram. A question on the diagram? Okay, so I'm going to stop here. I'll do another, I'm going to say a little bit more stuff next time, and then I'll do chapter 34. But before I go, I do want to show you the series LRC circuit real quick. So let me quickly show you the series LRC circuit. And I want to show you this because I can show you V in and V out. So I got to change cameras. Let me just vary the frequency. I had this set to 1,000 volts. 1,000 hertz. You can see the peak shift. I'm going to show this to you again next time. Unfortunately, I'm going to have to run. So let me stop here.